All right, then, here we are. So we're ready to get rolling. Today, all we have to do is carry on with chapter 12, our introduction to statistics. And so let's get back to it. So we've already covered, of course, the measures of central tendency, although not completely. There's still a couple of things to do, but we're largely done with it. So remember, the three are mean, median, and mode. And we saw that for each one, there are typically, but not always, different versions for populations and samples. And there's usually a formula, but not always, as we've seen. Like, for example, with the median and the mode, there did not turn out to be a formula, but there was a procedure that we were supposed to follow to calculate the median or the mode. So each of these has its own strengths and weaknesses, of course. We saw that the reason why medians can be very important is because our data may contain what we call outliers, which means values that are much larger or much smaller than the rest of our data. So let's go back. Oh, and also don't forget, we looked at the sample, the weighted mean as well. This is just a special case of the mean when we have a lot of repeated values in our sample or population, but it can come in very, very handy. And also, of course, we saw that this is how they calculate your GPA, so it's awfully useful as well as important. So, but yes, what I wanted to do is come back down here and remind you that the median is used when we have outliers in our data. For example, this case we looked at right here, clearly this element 100 is an outlier compared to the rest of the sample. So in a case like this, the sample mean would not be terribly meaningful. So instead, we typically would use the median. Most of the time we'll use the mean, but when our data contains outliers, then we'll probably use the median. Now, in the real world, sometimes we run into issues trying to decide what values are or are not outliers. But here we'll just assume that we recognize that these are outliers. And if so, then we'll choose to use the median instead of the mean. And then we saw that the mode has issues as well. It's probably the least used of the three. The mode just tells us how often or which numbers have been repeated the most frequently. And for certain cases, that might be very useful information. But often we do not use it with numerical data. And one of the strange things about modes is that there doesn't have to be a mode, and there can be more than one mode, which makes it very unusual. In other words, if we have a bunch of numbers where there's no repeated values, then we simply do not have a mode at all. And that makes things a little bit awkward. Imagine being told, well, what's my measure of central tendency? Well, we're using the mode, but there isn't one. So you have no information then. And then, of course, it's possible that there could be two modes. And for some applications, that could be extremely useful information. But often we would prefer to have a mean or a median rather than a mode when we're dealing with numerical data. So when is the mode very useful? The mode does have one advantage over the mean and the median. That means, or that happens when we have non-numeric data, or sometimes it's called qualitative data. In fact, I'm going to sneak that in here right now because that's an important definition. Okay, here we go, non-numerical data. All right, so what I'm going to do here is introduce a definition for us. And this is just for your benefit. So just in general, we say that numerical data is also known as quantitative data. Non-numerical data is also known as qualitative data. So when you hear those words, quantitative simply means numerical, qualitative is non-numerical. And so we've noted that the mode, and I'll put that in here as well, unlike the mean and the median, the mode can be applied to qualitative data. And that's one of the advantages that it has over the mean and the median. But most of the time, we do not typically use the mode unless there's an extremely good reason for it. It's usually down to the mean or the median. And even then, we typically only use the median when we have outliers. Okay. And again, a lot of it has to do with the properties of these three measures. The mean is easy to understand. And that's a big deal. That is actually a big deal. But also it has mathematical properties that are very convenient compared to the median and the mode. So for statistical applications, the mean is usually easier to deal with. So we try to use it whenever possible. But the median, it's good to know that the median is available if we have outliers. All right, now, what we're going to do next, and this is, I don't believe we got this far, we're going to look at the relationship between the three measures of central tendency. And it turns out that data in general can often be described as falling into one of these three categories. All right, we'll see what they mean in a second. We have negatively skewed, we have symmetrical, and we have positively skewed. Now, not all data falls into one of these three categories, but we can help identify which group our data might belong to by looking at the relationship between the mean, median, and mode. All right, now before we do this though, what I want to do is take a little detour for a second. Let me give you a second to catch up. I want to show you a graph that we will use in this section that's awfully helpful in helping us describe what data look like. All right, so just as a side detour here, we're going to throw this in. And so what I want you to see is a special kind of graph that you can use to describe your data, sample or population, either one is fine. And so it looks something like this. Imagine you have a collection of GPAs in a class. So I don't know how many students are in the class, but let's just say I'm interested in studying the distribution of their GPA. So here on the upper, the vertical axis, I have frequencies. And over here, I have on the horizontal axis GPA. And suppose I break up the GPAs into ranges. Let's try, for example, how about 0 to 0.5 to 1, 1.5, 2. I'm going to run out of space here. Hold on. 3, 3.5, and 4. Okay, so these are GPAs. Now, what I'm going to do is construct a bar for each range. So let's say there's one person whose GPA is between 1 and 1.5. So the bar itself represents this interval between 1 and 1.5. The height represents the number of students who fall into that category. And then we have two people who are between 1.5 and 2. And let's say we have 4 people who are between 2 and 2.5. And then we've got 10 people between 2.5 and 3. And then we have, let's say, 12 people who are between 3 and 3.5. And then finally, there's only one person in this range between 3.5 and 4. Well, this is not exactly an artistic masterpiece, but what I want you to be able to see here is that the bars themselves represent categories. These are categories, these are ranges of GPAs. Each bar represents represents a category or range of GPAs Okay, that's an important detail. Over here, I'll mention that the heights of the bars represent frequencies. So in other words, we can tell by looking at the bar, side the chart, how many people fall into each of these categories. Without having to see the actual numbers, we have this nice little graph, which tells us most of the students are between 3 and 3.5. A smaller number are between 2.5 and 3, and then it falls off quite a bit down to these lower ones. And then there's one person way up here in 3.5 to 4. So this type of graph is called a histogram. The name seems a little weird. It comes from a Greek word, which I looked it up once. It has something to do with the heights of masts on a ship. All right, so you can imagine these are ships with masts on them. So a histogram represents the frequencies of our data in such a way that we can see at a glance what the relationship is between these numbers and get a feel for the most common values. For example, you could see that this bar here could be thought of as the mode of this distribution. Okay, so the mode would be here because most of the students are in this category. We can't really tell for sure where the mean and median are without having more information, but most likely they're down in this area down here because that's about halfway between. Wherever we have the halfway mark, that would be the median. And then the mean could be almost anywhere in here. So the reason why I mention this now is because what we're about to do is based on histograms. And so what we're going to see is 3 different cases, and we can identify them by the relationship between the mean, median, and mode. Now, in the first case, what if it turns out that in our sample or population, the mean is less than the median, which in turn is less than the mode? Then we describe this situation as negatively skewed. You'll see why when we look at the histogram. All right, are we ready? Now, this illustration, this is for not GPAs, but the returns to stocks. Okay, so let's look at this graph for a minute. Now you can see, now this is how Excel makes its histograms. You can see by looking at all these numbers, in the bottom you see these are rates of return, and they can be negative or positive. All right, this would be 0, breaking even. And here's the unfortunate reality of this set. Most of the time our stock lost money. How can you tell? Because most of the returns are negative. These are all negative returns. These are positive. And so this person is not too happy right now with the performance of their portfolio. The majority of the returns are negative. So the mean, let's say it's hard to tell just by looking at this. The modes are up here. There's actually 2 modes because they're equally likely. Let's say the median is right about here, and I'm guessing to a certain degree. And let's say the mean is way down here somewhere. The reason why the mean is so low is because of all these large negative returns down here. So you can see right here, we can see or to observe that the data are negatively skewed because the mean is smaller than the median, which in turn is smaller than the mode. And you can tell at a glance just by looking at the data without having to look at all the individual numbers that this data is negatively skewed. All right. Now, what other cases are there? There's 2 more cases that we could potentially run into. Now, this next one is kind of interesting. What happens if all three of these numbers are identical to each other, the mean and the median and the mode? Well, then we have a situation which is kind of interesting. The data are said to be symmetrical, and the word symmetrical means there's a balance. It's almost like you could draw a line down the center, and the left and the right-hand sides are mirror images of each other. All right. So what does this graph look like? Ooh, now that's not bad. It looks kind of nice. There's like I said, there's a mirror image between the left and the right. They're absolutely identical to each other. And the mean, median, and mode are right smack in the middle. That's what it means to be symmetric or symmetrical. That means the gains have been balanced by the losses. I'm essentially breaking even with this stock. All right. So there's one more case to consider. And it's really just the reverse of the negatively skewed. This would be positively skewed. All right. So now this time the mean is the largest. It's greater than the median, which is in turn greater than the mode. And in this case, we say the data are positively skewed. So you can probably visualize already what this looks like. It's the reverse of negatively skewed. This is what we want when we're talking about stocks, big time. All right, what does it look like? Oh yeah, here we go. So now here's a happy investor. This is 0. These are positive returns. And these are negatives. So you can see there's more positive than negatives. So let's say the mode is here. The median could be, let's say, here. And the mean could be down here somewhere. So our data could potentially fall into one of these three categories. And this is important information to have. If you're an investor and you're thinking about buying, let's say these three graphs represent three different stocks and you're picking one of them, well, clearly this is the one that you want. Okay, so that's one way in which we could pick stocks, by looking at these plots of their returns and determining if they're positively skewed, symmetrical, or negatively skewed. Now, if the relationship is different, then our data do not fall into any of these categories. And that's okay. Not all data falls into one of these three categories. The data can get very strange, as a matter of fact. Like, for example, well, let me just throw this in here. What about a case that does not belong to one of these three categories? Let's say that if the relationship between the mean, median, and mode does not fall into one of these three categories, then the data are not symmetrical and they are not skewed. There's no name for this situation, by the way. It's just, it could be anything. So let me show you a graph which doesn't really follow any of these. Suppose you had something like this going on. Let me try that again. Well, you can see it's just a mess. There's just data all over the place. So this data is not symmetrical and not skewed. And so a lot of data falls into this category. So, but those are three special cases that we might run into. But the advantage of having those three measures is that we can tell right away which one they belong to, if any. All right, now, what we're going to look at next is another set of measures that are actually going to show us not where the data, the center is located, but how spread out the data are from the center. Now, what exactly does that mean? Let me just show you a couple of examples before I dive into this with our histograms. You can see that we could have two different data sets with the same mean, and yet the spread could be much wider. And so that's what these measures are attempting to capture. All right, so before I show them to you, let's look at a couple of graphs. So you can compare them side by side. Let's just say that these are two stocks that I might buy. Stock A and stock B. And let's say that the center represents 5%. But for this stock, this is what our returns look like. And for this stock, they look like that. Now, let's say they both have the same mean. Now, again, these are pretty crude drawings, but I think you get the point. Which one has the returns more spread out? Like, let's say, for example, this represents a loss of 5%, and this is a gain of 5%. Or even better yet, just to make it clear, let's make this negative and positive 10. This is, let's say these are like 5, 4, this is 3, 4, 5, 6, and 7. Okay, so the idea here is that here the stock returns, the range is between 3 and 7. So all returns are within. By the way, I guess I don't need these percent signs because it's already understood from the axis that these are percentages. That's right, we'll leave them there, but all returns are within 4% of each other. Whereas over here, wow, look at this. All returns are within 20% of each other. Okay, so they're not the same, are they? Even though they both have the same mean. And in fact, they both have the same median, don't they? And as a matter of fact, when you look at them, they're both symmetrical, aren't they? And yet, so in spite of the fact that they have the same mean and they are both symmetrical, or they're supposed to be based on my clumsy drawing, what's different about them? There's still something very important that's very different between the two stocks. And what would that be? Well, the returns in the stock on the right, stock B, are very far spread out, whereas the one on the left, stock A, these are awfully, awfully close to each other. So is that important to an investor? The answer is yes, very much so. Because, and this is something you'll need to think about when, let's say in 10 years when you're working full time and you've got money coming in and you've got savings and you want to invest them, all of a sudden you might find yourself analyzing stocks. And so what we'll note here is that because the returns to stock B are more spread out than for stock A, we say that stock B is riskier than stock A. Okay, this is because there is more uncertainty associated with the returns to stock B than stock A. In other words, if you look back at these graphs again, you'll see that with B, every year that goes by, you could gain anywhere from a loss of 10% up to a gain of 10%. Whereas with A, you're pretty much guaranteed to stay between 3 and 7%. So B is much riskier than A. And so this is important information to an investor. Very important. And so, even though we can see from the graphs that B is more spread out, it's not always so obvious. So we would like to have a quantitative method for identifying how spread out the data in a sample or population are, a number that we can look at and compare all these different data sets to each other side by side. So if I'm analyzing stocks, I want to know not only what their mean returns are, but I want to understand this spread feature as well, because that tells me how much risk is involved. All right, so with all that being said, there's 4 measures of dispersion that we could potentially apply to these cases just to help us understand how dispersed these numbers are. So here they are. Now, you may have heard of these too, but possibly not. So here we go. We've got 4 this time. All right. So maybe you've heard of these. The word range you've certainly heard of. The others 3, maybe not. All right. So luckily, the range is really, really easy. The variance and standard deviation are a little bit trickier, okay, than what we've done up to this point. All right, so let's begin with the range. The range, as you probably knew already, is simply the difference between the largest and the smallest element in our either sample or population. Like, for example, what if I wanted to know, let's just do one quick qualitative example. Suppose that we are shopping for let's say we need a new couch. Okay, we go to Macy's and they have 8 different couches to choose from. Okay, the cheapest is $400 and the most expensive is $2,000. Okay, so the range of prices for these couches is 2,000 minus 400, which is, whoops, 1,600. Okay, now that doesn't tell us which one to buy, but it does tell us that the range of possibilities is quite wide. We've got everything from the cheapest to the most expensive and everything in between. So the range is simply the difference between the largest and the smallest. All right, and there's a lot of applications for this. Here's one that we can do with actual numerical data. We've seen this one before. These are the elements we had in the sample that we've been using since the start of this chapter. Anyway, so just like with the median and the mode, we have to sort these elements. And once we do, you can see that all we're doing is taking the difference between the largest and the smallest, which is 6. Now, don't forget, when you subtract a negative number, it becomes positive. All right. And that's it. That's all there was to it. Just the difference, which is 6. All right. Now, just like with the median and the mode, the calculations for doing this are the same for the population and the sample range. And in both cases, there is no formula. This is a procedure. Okay. Which means sort the data to calculate the difference between the largest and smallest elements. And that's all you have to do. All right, now, having said that, the next measure that we're going to look at, we're back to the case where we have to make a distinction between a sample measure and a population measure. And in addition, there's a formula involved. And the formula involves our old friend, the summation operator. And in fact, it requires one of the more complicated cases that we saw for the summation operator. So don't be too horrified when you see it. It's not as scary as it looks. So let me put it that way. But it is a multiple step procedure. Okay. So, but we've already had some experience with the summation operator. So it should be clear pretty quickly what we're supposed to do. All right, so with all that buildup, let's take a look at the sample variance formula. Ooh, okay. Well, now we're getting into some tricky territory. So S squared is used to represent the sample variance. And if you notice, S is a Roman letter. It is used to describe a sample. So the sample variance this is a single sample element. This is X bar is the sample mean. And this, of course, is the sample size. Now, the problem is, what exactly are we supposed to do here? All right, well, when we're ready, we're going to go through an example and you'll see what we're doing. But I think I should write it out in English, what we're about to do first. Okay, so let me give you a minute to catch up. All right, so let's copy this into another slide. And just see what exactly is going on here. Okay, so let me grab this and bring it over here. I'll just sneak it up here for the time being. So they're asking us to do this. For each sample element, subtract the sample mean, square the difference, and then add up the results. At the end, divide by n-1. Okay, so that's in a nutshell what we're doing. For each element, subtract the sample mean, square the difference, add up the results. When you're done, divide by n-1. It doesn't sound that bad. Okay, so let's do this first example. Now, the first thing we need to do is calculate the sample mean. Now here, we already had done this, but the first step is always to calculate the sample mean. So here it's 2. You might recall from the beginning of this chapter, this is the same data set we've been using all along. Now what do we do? All right, so let's get the formula back. And oh, by the way, you know what I'm going to do too? Let me copy these numbers. See if I can sneak them in here somewhere. Ooh, well, that turned out very strangely. Yeah, just so you can see them up here, I've repeated the numbers. And so what we're doing here is we're going through, and you'll see, for example, this is x1, and this is x bar. I'm subtracting them and squaring them. Now here, I've got x2 minus x bar squared. What do I have over here? x3 minus x bar squared. Then I've got x4 minus x bar squared. And then finally, this last one is x5 minus x bar squared. So here I'm just plugging in the numbers. Now also, if you notice, n is 5 because there's 5 elements. And that means that n minus 1 would be 4. So that's why 4 is in the denominator. Now, the next step is simply to calculate these. What I usually encourage people to do is calculate what's inside the parentheses first before you go any further and square them, because that way it's harder to make mistakes. In a case like this, one of the big problems with this formula is that it's so easy to make mistakes. So in fact, why don't we do it right here? That means you've got 0 squared plus minus 3 squared plus 1 squared plus 3 squared plus negative 1 squared, all divided by 4. Now that shouldn't be too hard. Or at least let's say it'll make it harder to make mistakes. Now, once that's done, of course, you'll calculate the squares and then add them up and divide by 4. All right, so what does that turn out to be? In fact, maybe I could copy this into the next slide. Let's try that. Just for reference. Okay, so you can see how that turns into here, 0 plus 9 plus 1 plus 9 plus 1 over 4. That equals 20 over 4, which is 5. So s squared equals 5. That's your variance. Now, there's one major problem with this variance measure. What could that be? Well, I'll throw this in here. One major drawback to the variance measure is that it is measured in what we call squared units because of the way it is calculated. Okay, now, what do we mean by that? So in this example, suppose that the data represent temperatures in Celsius. Then the variance is 5 degrees squared. What does that mean? Well, that's just the whole point. There is no meaning to a squared temperature. So that's a real problem, isn't it? So what do we do? Because squared units are difficult to interpret, we can apply the next measure of dispersion, the standard deviation. Okay, the standard deviation is the square root of the variance. This eliminates the problem of squared units. Okay, so in other words, the variance is fine as far as it goes, but because it gives us squared units, which are awkward to work with, we've created, statisticians, I should say, have created this measure, which is an extension of the variance, called the standard deviation. And what we do here is we simply take the square root of the variance that we just got through calculating. And so the result will be a number which is in the same units as the underlying data. In our case, that would be temperatures. So this, like I said, the sample standard deviation then is the square root of the sample variance. And so, in other words, here's the formula, and you can see all we did was take the square root of the variance formula. So that could be written like this. Now, S, if you notice, S squared is the sample variance. S is the sample standard deviation. They didn't give it a new symbol because it's just the square root of the variance, so therefore we just call it S. Okay, so in our case that we just got through doing, since we already know that sigma squared, S squared rather, is 5, S is the square root of 5, which is 2.236. So this is degrees squared. And this would be degrees. And so all of a sudden now that's fine. So we can have a mean of 2 degrees and a standard deviation of 2.236 degrees. So anytime you have a variance, you can now turn around and calculate the standard deviation. Now, it would be nice if we could calculate the standard deviation directly. We can't. We need to start with the variance. So we usually end up calculating both at the same time. This, as it turns out, is by far the most useful of all the measures of dispersion. We see it everywhere. And in fact, we could apply it back to that stock example we had earlier if we had the original data, because now we know how what the numbers are, and we could compare directly the standard deviations of the two stocks, and now all of a sudden it becomes clear which one is riskier. All right, so let me throw you in here another example here. So that's our temperatures example. So with our stocks example, suppose that we have the following data. Here's stock A, stock B. Mean standard deviation. I'll abbreviate that STDEV. And let's say that, just as we saw before, they're both, the mean is 5%, but the standard deviation for stock A is 10%, and for stock B, it's 25%. So now we didn't have the original data. We couldn't do it ourselves, but let's just say this is what we ended up with. And you can see at a glance that stock B is clearly riskier than stock A. All right, how can you tell? Because it has the higher standard deviation. As you can see, this is a very potentially useful measure that helps us identify the risk. The mean we can see for ourselves is the same, but stock B is clearly riskier because we know that the standard deviation is higher. So you can see it's a very useful measure. All right, now with all that being said, now this again, we haven't seen this in a while, but here we do need to make a separate formula for the population variance and the population standard deviation, because they're not only are the does it have slightly different notation, but the formulas themselves are slightly different. So let me show you these side by side. The population variance, I'll just put the old one here so you can see it side by side. Oh, they are different, aren't they? So first of all, we're introducing a new Greek letter here. Now, this is interesting. This is the Greek letter sigma. Now, isn't it true, though, that this is also sigma? Yes, it is. So what happened here? Well, this is the upper case, and this is the lower case. So they're both sigmas. One is the upper, and the other one is lower. Then here's our old friend mu, our population mean. And of course, remember, capital N is the population size. And that's true here too. Now, as far as the actual calculations go, though, there is one subtle difference between the two, which hasn't happened up to this point. Let me point your attention to the denominators. Ooh, wait a minute. They're different. They're not much different, but they are different. And that was not true for other cases, was it? The only difference between the population formula and the sample formula was the notation. Now, all of a sudden, there's a slight numerical difference as well. Okay. Now, we're not going to do a separate example for this one just yet. Later on, when we're doing our practice problems, we will. But for now, I just wanted you to see the difference between the two. They both mean the same thing. They're both a measure of dispersion, but one is applied to populations and one is applied to samples. Now, of course, the relationship between the variance and the standard deviation is the same here as it was for the samples. So therefore, when we go to calculate the population standard deviation, we're literally just taking the square root of the population variance. It's so easy. Watch this. Oh yeah, there you go. So the population standard deviation is the square root of the population variance. The variance of the population has the same problem as for the standard deviation. In other words, it has squared units. So whether we're dealing with a population or standard sample, we always prefer to use the standard deviation. All right, so now we're ready to move on to our final measure of dispersion. And this is actually a combination of measures that we already know. It's not really brand new. Okay, so the fourth measure that we're going to consider here is this coefficient of variation. And this tries to take into account two different measures. It's considering both the spread and the location or mean of a sample or a population. So sometimes it's known as a measure of relative dispersion because we want to see how spread out the numbers are relative to the size of the mean. So what does that even mean? You'll see in a second. All right, here we go. So the general approach is you're going to take the standard deviation, you're dividing by the mean, and you're multiplying by 100 to turn it into a percentage. All right. So in other words, for the populace, well, let's do them both. So if you had a sample, that would be your formula. For a population, it equals sigma over mu. And you can see it's the same formula in both cases. The notation is the only thing that's different. All right, let's look at a case here. We've got two portfolios of stocks, A and B, and let's treat them as populations. And what we're going to do is calculate the CV, or coefficient of variation, for both of them. Okay, so let's treat them both as populations. And we're going to be given some information about their means and standard deviations. We won't have to calculate them ourselves. Let's put it that way. All right, so why don't we begin by assuming that the mean of stock A, or I should say portfolio A, is 8%, and the standard deviation is 16%. If you notice, the little subscript tells me that this is the mean of A, and this is the standard deviation of A. The reason why we need that is so we can tell it apart from B. Okay, now for B, Instead of 8 and 16, we have a mean of 10%. And we have a standard deviation of 30%. Now, I also want to mention one more thing. You notice how I've converted these percentages into decimals. That is usually the best approach. It helps us avoid mistakes. Okay, so even though it says 10% and 30, I've converted them into 0.10 and 0.30 just because it usually makes it harder to make mistakes that way. All right, now what are we going to do with these numbers? We're going to calculate this coefficient of variation. So for A, it's a very simple approach. We've got the standard deviation divided by the mean gives me a ratio of 200%. So the risk, by which I mean the standard deviation, is double the return. The mean equals the rate of return to that stock. So that means the risk is twice as high as my return. Now for the second portfolio of stocks, we plug in the numbers and we get 30 over 10. So therefore we get 300%, which means the risk is triple the return. Now, with that being said, which portfolio of stocks is riskier? Well, which one would you prefer? Well, because in the second case, the risk is so much higher compared to the return. That indicates that we should probably pick portfolio A because we only have twice as much risk as return, whereas in B, we have 3 times as much risk. That doesn't mean you have to buy that. I mean, you can do whatever you want, but at least we know that stock B has a lot more risk compared to its return than stock A. And so therefore, we might want to think about buying A. But the measure itself is a good way of comparing two stocks or anything based on the risk relative to the return. And that's very useful with financial securities like stocks. All right. Now, it turns out that there's actually another set of measures that we would like to consider, but these are different because instead of looking at the properties of a single sample or a single population, we're going to be looking at the relationship between two different samples or two different populations. And this will prove to be extremely useful for a lot of applications. The only problem is these are fairly complicated to calculate. Yeah, they are. There's no getting around it, but they're closely related to what we've just been doing. They're not completely different. So let's introduce the two of them. They're referred to, first of all, they're called measures of association. And essentially what we're trying to capture is the tendency for these two variables or samples or populations to move in the same direction. So I'll explain what that means in a minute. So their names are covariance and correlation. They're very complex ideas, but we can illustrate them with some graphs to give you a better feel for what they're all about. All right, so I'd like to give you some examples to give you a better sense of what we're trying to capture here. All right, so let me just give you a few quick examples. Suppose we are studying the relationship between how much time students study every week and their grade point averages. Well, in a case like this, we would expect that more studying leads to higher GPAs. Okay, so in this case, there is a strong tendency for both these variables to increase or decrease at the same time. In other words, the more you study, the higher GPA, but the less you study, the lower it should be. So our measures of association can give us a number that essentially tells us how strong this connection is. In other words, it isn't necessarily the case that doubling your study will double your GPA, for example, but there's a tendency for more studying to contribute to higher GPAs. And so we'd like to know how strong that connection is. And that's what these measures will let us do. On the other hand, when we're studying this relationship, suppose we are studying the relationship between how much time students spend texting and their GPAs. We would expect that more texting time leads to lower GPAs, and vice versa, of course. In this case, there is a strong tendency for the two variables to move in opposite directions. In other words, we're saying that when one goes up, the other tends to go down and vice versa. And so again, these measures of association would enable us to not only figure this out, if this is true or not, but how strong is this relationship? It might turn out, for example, to be that the connection is fairly weak, or it could be very strong. We don't know without looking at the data. Now, here's another one, which could have come up. Suppose we are looking at the relationship between the heights of students and their GPAs. In this case, we do not expect to find any connection at all. In other words, the two variables are unrelated to each other. Okay, and so again, this is something we could identify with our measures of association. And so if this is true, if there's no connection between heights and GPAs, then we would expect to find that or find this out from our measures of association. So really, there's three basic situations we could potentially find when we measure or use these measures, where the cases where the two variables tend to move in the same direction, opposite directions, or are completely unrelated to each other. Now, it turns out that there's this wonderful graphical device that we can use to study these relationships before we do any calculations. And these devices, or these graphical devices, are called scatter plots. All right, so scatter plots are awfully useful to help us understand what connection there is, if any, between two different variables. Such as studying time and GPAs. And so we would like to look at these before we do anything else. And so what do these scatter plots look like? Well, let me show you a quick example. Let's think about the connection between, let's say, GPAs and studying time. Now, the way this plot works is we have the XY coordinate system. And what we're going to do is assume that we have gathered up information, which, by the way, X is studying time. And I'm going to make a note here. You may remember this from high school. This is the dependent variable. I'm sorry, the independent variable. What am I saying? And Y is GPA, which we call the dependent variable. And the reason why we say that is because it should be clear that GPA depends on our studying time, not the other way around. So what we've done is we've gathered up data about a bunch of students. We wrote down their studying time and their GPAs, and each point on this graph will be a single student's information. Like this point could represent a student who studies 5 hours a week and has a GPA of 2.9. And this, for example, could be a student who studies 8 hours a week and has a GPA of 3.1. So each point or dot on the plot is one student's GPA and studying time. And so we plot them and we see what we get. Now, in this case, by the way, these numbers have to be positive. So we are restricted to the first quadrant of this graph, but let's say this is what we get. So if you look at the points carefully, you'll notice that if I were to draw a line between them, trying to connect the points, that line, which is known as a trend line, the trend line has a positive slope. which implies there is a positive connection between X and Y. Which is what we expected. So the point of this plot is that you can just glance at it and say, oh yeah, you're right. When X goes up, Y goes up as well. Now, if you notice though, they don't always go up by the same amounts. The points are scattered around that line. Now, why is that? Because studying time is not the only thing that determines your GPA. Other factors can get involved as well. But for the most part, more studying should lead to higher GPAs. So that's a classic example of a scatter plot. Now, if I were to do the same thing for GPAs and texting time, well, then the plot should look very different. What do I mean by that? Well, remember here, we're assuming that when people text more, they're wasting time and they're not studying. You know people who just constantly have their fingers on those buttons. They never stop. And so how much studying are they really doing? It's, obviously there's more going on than just texting. But in general, the more you waste your time with frivolous things like texting, the less time you have for serious activities. So this plot will look very different. Okay, so we don't have to re-explain everything here. We'll just note that this example is GPAs and texting time. And so this time the points will go in the opposite direction. So the trend line has a negative slope. The variables tend to move in opposite directions. Okay? And this, I hope, makes perfect sense. So we can say that there is a negative connection between X and Y. Now, let's consider the third and final possible case, GPAs and heights. And we're going to see what that would look like because we know already that there's no relationship there. All right, so let's do one final example. Oh, by the way, I did forget to do one thing. I just want to remind you, this is GPA and this is texting time. Okay, because we assume that the texting time is determining the GPA, not the other way around. All right. So here then, I want GPA to be Y and height to be X. Now here, of course, you're going to get some tall people with high GPAs and some tall people with low GPAs. And with relatively short people will have high GPAs and they'll have low GPAs. And so there's literally no connection here. The trend line is flat. The trend line has a slope of 0. So this means that there is no connection between the two variables and we say that X and Y are independent of each other. So those are the three basic cases that we want to consider. Now, the measures themselves are just helping us understand the quantitative relationship between them. But here, at least, we intuitively understand what this means, I hope. This is what we're trying to capture, and this is useful for an awful lot of different applications. All right. Now, probably you're aware, if we look at the calendar, it's hard to imagine, but May is right around the corner. In fact, let's get ourselves a calendar out here. April, oh, that's January. Let's try this. No. Why are they doing this to me? Let's pick one that actually tells me April. Wouldn't that be nice? All right, there we go. So this coming Friday is the last day of April. The following Monday, oh no, I want May. And this one shows that next Monday is the 3rd. I don't know if you're aware of it, but we're off on Monday, the 3rd. Remember, they randomly picked 3 days to give us off to make up for the loss of spring break. That's one of them. It seems a little strange. Wait a minute. What just happened here? Oh, not enough days. That's right. You mean days off or days of school? Anyway, it's here somewhere. I just want to, it's written down in case you weren't aware of it. Monday, May the 3rd. So those are the 3 days that they randomly chose to give us off to compensate for the lack of spring break. So that's Monday. So what I'm getting at here, the bottom line here is that we're not meeting next Monday. So that being the case, what I would like you to do is, even though we're not done with this chapter, I would like you to get the chapter 12 problem set, which is on Moodle, and work on it between now and Thursday. You will not be able to finish all of it because we're not completely done. But I want to get as far as we can, given that we're off next Monday. Okay, so in other words, in order to avoid wasting time, let me just double check. By the way, they changed this on us. Let's go get Moodle open. And just to confirm that the chapter 12 problem set is here. Why, there it is right there. Okay. And it's just asking you to do what we've been doing. So it should be okay. All right. So what I'd like, as soon as we're done with the chapter, I would like to go over these problems on Thursday to make sure we're all caught up. Now, also, I just want to point out that the final exam is based exclusively on chapters 11 and 12. So what comes after this is the sample final. And when that's done, we're done. And so I can give you the final as soon as we're done. We don't have to wait till the finals week, which is something like May 13th. So if you want to finish early, that's fine with me. That's, if you certainly can feel free to wrap up your this class early, because by the time we're done with that, I'm guessing that we'll be completely finished by Thursday. This, well, maybe not. You know what? Maybe we may still need the 10th, but that's it. I mean, we don't need to wait till the 13th to start the final exam. All right. At the very latest, we'll be done by the 10th. And so that way, maybe it'll give you a little head start. No, I don't. Well, maybe I did. I'll look for it. Wait till we're done and we'll discuss it. But anyway, so either the 6th or the 10th will be done, and I can give you the final, and then we'll be done. All right, because there's no more new material. When we're done talking about our measures of association, that's it. We're finished. So why don't you get the, download chapter 12, problem set, and take a look at it, and then we'll wrap that up on Thursday, and then we'll have Monday the 3rd off, and then we'll finish up everything possibly on the 6th, if not on the 10th, and that's it. We're done. Woohoo! Oh, the usual. You'll have a week or so. Plenty of time. In fact, yeah, no, that should be it. It's really no longer than any of the other ones because it's just the 2 chapters. So yes, you'll have plenty of time. All right, so if there's nothing else, I guess we can stop right here, and I'll see you all on Thursday. Don't forget to do the chapter 12 problem set. All right.
Thank you, Professor.
Okay. All right. Okay. Let's see. All right. I'm going to look up in my email account. Okay. It must have gone to my other account. There we go. All right. Let me see what I've got here. Oh, well, the first midterm, your grades should be in the grade book in Moodle. Did you know that there was a grade book? Yeah, I posted them all in there. And also, if the midterm is too large, how you can break it up into little pieces. Is it a photograph? Is that what the problem is?